Hey guys, BuildZoid here, and today we're going to be taking a look at the various voltages involved with DDR5 overclocking on Intel 12th Gen CPUs. Now there's quite a lot of them, so we're just going to get right into it, starting off with the VCCN rail, which typically is generated over in this area of the motherboard. So yeah, we have VCCN. That then goes to your CPU's integrated voltage regulator, which then converts the VCCN voltage into VCCSA, CPU VDDQ. I like the MSI naming convention for this one. This voltage has like a million different names. We're going to go over them. Anyway, we're not going to get into that just yet. Yeah, so VCCN goes into the integrated voltage regulator, gets converted into VCCSA, CPU VDDQ, as well as CPU VDDQ, and a bunch of other minor voltages that are not in the scope of this video. By spec, the VCCN voltage is 1.8 volts, and we're going to say safe for long-term use, you can go up to, say, 2 volts. And the thing is, you really shouldn't have to adjust the VCCN voltage like ever, because the only reason that you would want to adjust the VCCN is if you're running one of these two voltages really high, as the integrated voltage regulator generally has a optimum sort of voltage range in which it likes to operate. So the stock voltage of 1.8 volts, it's converting typically down to like VCCSA at stock is less than a volt. So, you have this big gap between the input voltage and the actual VCCSA rail. Now, if you're pushing, say, north of 1.5 volts on either of these two, it might be slightly beneficial to bump the VCC in a little bit. But under most circumstances, it really shouldn't do anything. So you can mostly just kind of ignore this voltage. Also, the reason why I say safe in quotation marks is because there's obviously no official recommendation from Intel. As far as Intel is concerned, any kind of overclocking is a violation of the warranty, and that includes enabling your XMP profile, because it's extreme memory profile, not stock memory profile. Anyway, so the safe voltages that are here are just guesstimates on my part, and that's kind of that. Anyway, let's talk about voltages that we do kind of care about, which would be VCCSA and the CPU VDDQ. So VCCSA stands for is your system agent power rail. At stock, it is 0.9 volts, and it powers the CPU's system agent, which is the thing that sort of connects everything inside your CPU. It connects the memory controller to the ring, it connects the PCIe to the ring, it connects basically everything. It's sort of Intel's equivalent, it's basically the replacement of the North Bridge, is what the system agent is. The main reason to raise the system agent voltage is if you're running high memory controller clocks. However, on DDR5, that isn't really a thing, because with DDR5, you're typically going to be running in Gear 2, and so your memory controller is going to be heavily underclocked relative to the memory clock. So really, this is more of a DDR4 thing where you need potentially a lot of VCCSA. But if for whatever reason you need high VCCSA for your, DDR, I guess you could also use this as guidelines for DDR4 to some extent. So, so far it's mostly the same. We'll get to the part where DDR5 is very different eventually. Anyway, so safe for long-term use, I would recommend that you stay below 1.45 volts for VCCSA. And really, in my experience, there's no reason to for DDR5, there really is no reason to hit even 1.45 volts. I've mostly been using 1.35 volts VCCSA or even less than that. In fact, if you're running slower DDR5 kits, you can get away with even less than a volt for VCCSA, and it really isn't an issue. And by slower, I mean, less than 6,000 megabits per second. Even 6,200 megabits per second, you can get away with 0.95 volts of VCCSA or around 1 volt, and it'll be just fine. So this is a voltage that you really shouldn't have to raise it too much. And generally, if you're pushing your memory pretty hard, you're probably going to end up at somewhere around 1.3 volts, and that's going to be just fine. So, yeah, anyway, moving on from VCCSA, we got CPU VDDQ. Now, this rail is awful, mostly because of the naming conventions surrounding it. So, I like the MSI naming convention, which is CPU VDDQ, but it's also called VCC VDDQ. which is just an awful. I've not even decided which way I want to write it. The thing is, I've only ever seen it called VCC VDDQ in some Intel documentation, and yeah, maybe ASRock uses it in their BIOS. I don't know. I've not seen an ASRock BIOS yet. Anyway, so yeah, VCC VDDQ. Asus calls it like, I think they call it like memory VDDQ TX. And then there's Gigabyte, which they have the worst. Because the thing is, so Gigabyte doesn't directly refer to this voltage in their BIOS. Instead, they have this really dumb setting called DRAM VDD/VDDQ. And this setting, and I can't believe we're getting into this, but I guess here we are. Imagine if Gigabyte had sensible naming conventions. I mean, the same can be true for a set of like Asus motherboard BIOSes. Like Asus measures resistances in clock cycles because that makes sense. Anyway, DRAM VDD/VDDQ on Gigabyte. So the thing about this on Gigabyte boards is that setting actually is a combination of CPU VDDQ, memory. So I'm just going to put MVDDQ for the memory, memory VDD, and it also sets your VDD2 voltage, which we're going to get to eventually. So the thing is, in Gigabyte BIOS, you have separate settings for these three. So if you set these manually, this setting ends up only controlling the CPU VDDQ voltage. And this doesn't make any sense. Like, on no... there's no logic to why you would ever implement your CPU VDDQ voltage control like this, but Gigabyte BIOS is just very special. So, that's kind of that. I'm sure whoever at Gigabyte came up with this voltage control would get along really well with the guy at Asus who decided to measure resistance in clock cycles. Because, like, this doesn't make any freaking sense. Anyway... which is really unfortunate because this voltage is rather important. So CPU VDDQ, and I will continue to refer to this as CPU VDDQ because the MSI naming convention makes the most sense to me. It tells us where the voltage is. Doesn't really tell us what it's for, though. It's a memory controller voltage. Unfortunately, I really can't get any detailed documentation on what exactly this voltage does. It has very strange behavior on Asus motherboards, specifically. Where it needs to be like as high as your memory voltages, which is super weird because on every other manufacturer I've been able to run it really low relative to the memory voltages. Anyway, yeah, so this runs something in the memory controller. It is not used for communicating to the memory. There's a separate voltage that actually handles communication to the memory. And so, yeah, I guess the best way you can think of this is sort of like a VCCIO2 rail, which is what we had on Z590 with 11th gen. You had a VCCIO2 rail, which greatly affected memory overclocking. CPU VDDQ is kind of similar to that. At stock, this sits at 1.1 volts. I would not like this. The thing is, this is a internal like CPU voltage rail. And so I would not recommend going over 1.45 volts on this. However, if you have an Asus motherboard, you're probably going to end up in a situation where if you try to run... Well, depends how hard you're pushing your memory. But if you're trying to really push your memory on an Asus motherboard, this right here, like, you're just going to end up violating this. There's nothing you can do about it, in my experience, because the boards just don't train. So, yeah, if in a couple years, like, your memory controller goes and you have an Asus motherboard, that's why. And the thing with memory controllers is, like, in my experience, they don't tend to give warning signs that they're about to fail. It's just kind of like suddenly one of your memory channels is gone, is my usual experience with memory controllers failing. Is just like, oh, you're doing your thing, running high voltages, and then suddenly, where's my where did half of my RAM go? And then you find out that the memory channel is just gone. So, yeah, like, if you have an MSI or Gigabyte motherboard, you can just sort of stick to this and you'll be fine. In fact, you can go even a lot lower than this because, yeah, it's an internal memory controller rail. But on Asus boards, you're kind of boned, in my experience. Like, yeah, I tried really hard to not go over 1.45 volts with my Apex, and it just wouldn't train. So, um, yeah, not really sure what to tell you about that one. So yeah, because the thing is, like, I can't get any, like, obviously Intel doesn't have an official recommendation for what's safe for this. It is a memory controller rail. Like, there's a decent chance that 1.5 or even 1.55 volts might not be that dangerous, considering this rail does start at 1.1 volts as stock. But yeah, I don't know. Like, it's an internal CPU rail, and I don't really feel comfortable shoving more than 1.45 volts into anything that's internal to the CPU. Um, yeah, not for like long-term use. So that's kind of that. If you're feeling brave, I'm going to add that for this one. If you're feeling brave, or if you're willing to replace your CPU every year, 1.55 volts is probably okay. Probably. Um, anyway, let's move on to the next voltage rail that goes to the CPU, which is the VDD2 rail, which lives over here. Yeah, which doesn't really make a lot of sense that it's all the way over here. And the reason it's all the way over there is that's the voltage that's actually used for communicating with the memory, which makes zero sense because you got VDD. Like, when I first saw the name VDDQ, I was like, oh yeah, data queue. This is what's used for the memory, right? And then TX is like, oh, for transmission. No, this is not used for communicating with the memory. All of the memory, like, signal high, signal low definitions are relative to VDD2. Anyway, so VDD2 sort of just comes under your memory sticks and into the CPU, as in literally these capacitors right here are VDD2. So yeah, fun fact about that. This is actually not that different from what you see, like DDR4 motherboard. Like, for DDR4, this is standard, except on DDR4 you don't have a bunch of voltage regulators on your actual memory stick as well. So anyway, VDD2 at stock is 1.1 volts, and this is a external voltage rail. Like, this powers the physical, like the PHYs of the DDR5 memory controller. It replaces the VDDR rail for DDR4. In fact, if you've got a DDR4 motherboard, this is literally what, like, that VDD2 is like the replacement for the DDR4 power rail. So with this one, you can actually get away with really high voltages. I wouldn't be worried about shoving even 1.6 volts into this, because, like, there's DDR4 kits that'll literally set your equivalent of this to that. So yeah, that's an external voltage for the, like, for communicating with the actual memory. However, you won't necessarily want to set it very high. And the reason for this is because VDD2 is actually used for, like, straight up signaling to the memory. And so if you set it too high, you end up with, depending on what BIOS, like what motherboard you have, what memory sticks you have, what BIOS you're on, there's going to be a sweet spot for VDD2. And it's never 1.6 volts. I've never not had a scenario where 1.6 volts of VDD2 was actually a good idea. As in, it didn't help stability. Typically, it actually harms it, especially on the 1T command rate BIOSes. You actually end up wanting to run less VDD2 rather than more, in my experience. So this really likes to sweet spot, and typically that'll be somewhere in the range of... So that'll be typically somewhere in the range of like 1.2 to 1.45 volts, and I've run out of space on the screen, so that's great. But yeah, so somewhere between 1.2 and 1.45 volts is probably going to be the sweet spot. Usually what in my experience is, like, when you switch over from 2T command rate to 1T command rate, it actually wants to be lower rather than higher. So that's super weird, but yeah, so that's kind of that. Like, it's not too surprising. On DDR4, you can actually find quite a lot of memory sticks, which more common on the memory sticks using PCBs that aren't really optimized for raw speed. A lot of them will roll over super quickly. If you just, like, if you're pushing them for memory speed and you just mash voltage into them, they'll very quickly roll over, and you sort of end up having to use less voltage rather than more in order to stabilize high speeds. And so DDR5 kind of exhibits that same behavior, because DDR5 is always fast. Like, there is no really slow DDR5, right? It starts at 4800 megabits per second, which Like for DDR4 is well into like weird behavior territory. And so DDR5 basically just exists at weird behavior territory. There's no normal zone for DDR5 in my experience. Yeah, so VDD2 is one of the like this one's cool. Like you don't have to be worried about this one because you're not going to be pushing it super high because there's never any reason to, or yeah, there's not really any reason to push it super high in my experience. Yeah, so that one's neat. Well, actually, there are some BIOSes with 2T command rate where it helps to be at like 1.55 volts, but I wouldn't be worried about that one because literally it replaces the DDR4 power rail that would go to the CPU, and it's just used for driving signals to the memory sticks. So that's VDD2. The main thing is, again, it's sweet spots. So this is kind of the one where I'd probably start at like 1.35 volts, and then I'd test if you can like go up, go down, see what works. If you get it really wrong, it probably won't train. So that's kind of neat. Anyway, let's get on to the actual memory stick. So on the memory stick, we have this lovely chip called the Power Management IC, or PMIC for short. And this generates a bunch of different voltages, but the only ones I care about, and you should care about, are the memory VDD. So MVD, actually I'm going to put them like on different sides or I'm going to run out of space again. So we have MVDD, so memory VDD, and then memory VDDQ. And I can't write as fast as I can talk, which shouldn't be that surprising. So memory VDD powers the actual sort of core of the memory, is like, yeah, powers the core of the memory. There's not really a better description I can give you for that. If you're not aware of the like architecture of memory chips, we're not going to get into that. But this powers the memory core. It's stock at, man, that I'm zooming in way too much. So it's stock at 1.1 volts. And safe for this one, it depends on the memory chips. So we're actually going to use the Brave value again. So we have safe is, definitely 1.4 volts. In fact, yeah, like 1.4 volts. There's a lot of memory sticks that won't even let you go much past 1.4 volts anyway. So that's kind of neat. Is like if you just want to be safe, you just go up to the sort of normal voltage limit for the power management IC. And then if you're feeling brave, and mainly if you have like SK Hynix based memory chips or Samsung memory chips, you can go up to like 1.6. It is worth noting that DDR5 runs rather hot, and so at 1.6 volts, you're going to want a fan on the memory sticks, or, well, actually, if you let the memory get too hot, that will cause it to degrade. Straight up, you can kill DDR5 by getting it too hot. And especially at high voltages. So that's something to consider. But basically, yeah, if you're going to be in the Brave voltage range, I highly recommend that you zip tie a fan directly to your memory sticks. Water cooling is also an option. And so that's MVDD. And this runs so like I mentioned earlier, it powers the core of the memory. It primarily, it affects both your memory speed and your timings. And then the big difference to MVDDQ over here is that MVDDQ is the actual I/O of the memory. So this powers the part of the memory that actually talks to the CPU. Whereas this basically handles the shuffling of the data inside the memory chip itself. This handles sending off sending the data to the actual CPU. And so this voltage primarily affects your memory speed. It can sweet spot to some extent. So yeah, and but in terms of actual voltage behavior, it's sort of the same thing. At stock, it's 1.1 volts. If you want to be safe with it, you're going to stay at like 1.4 volts or less. If you're feeling brave, you can go up to 1.6. There's really not much more to it than that. And if you're if you're feeling brave, you can go up to 1.6. And in my experience, you can, the thing is, this will actually sometimes sweet spot to some extent, and you want to keep your MVDD and MVDDQ relatively close to each other. The official specifications for DDR5 say that these two voltages should never be more than 200 millivolts apart. during like startup, and then during regular operation they should never be more than 66 millivolts apart. Now, I believe the 66 millivolt limit is more to be within that 1.1 volt tolerance range, right? Because if your MVDD or MVDDQ are more than 66 millivolts apart, there's probably something wrong with your actual stock voltage. Like, your voltage is just completely out of spec anyway, so that's not really too much of a concern. So for general use, I would generally keep these within 150 millivolts of each other. If you have too much of a gap between these two voltages, the risk is that you're going to start having currents flowing in parts of the memory chip where there isn't really supposed to be current flow. So that's why you don't really want to set, like, say, 1.6 volts VDD with, say, a 1.1 volt MVDDQ. This would potentially kill your memory chips. It probably will cause them to, well, yeah, that could potentially kill your memory chips. I've not tested it. I don't recommend that you try it because, yeah, you could end up having, like, current flowing through the memory chip in weird places, and that could then damage it. So what would be sort of sensible, and what I've actually sort of used, is, like, say, 1.6 to 1.5 or even 1.45. I'd say this is kind of pushing it, but this should still be relatively okay, because the memory chips are allowed to be turned on with a 200 millivolt gap. So I can't assume that that would be too dangerous to the health of the chips. Though the DDR5 specifications do say that you should never have more than a 300 millivolt gap between VDD and VDDQ. So yeah, that's kind of that. So what I've actually, like, somewhat regularly used is something like 1.55 and 1.45. And the main reason you would do this is you want a relatively high VDD to get low timings, and, you know, at high mostly low timings. The speed doesn't really care that much about the VDD voltage. And then the VDDQ, on, say, the 1T command rate BIOS, it actually sort of sweet spots at 1.45 volts-ish for me on the Tachyon. So straight up, it's just kind of like, this is actually kind of the best voltage to run it at anyway. And also on some, like, even then on, like, 1.5, 1.55 volts, if you're feeling lazy with your memory settings, you can just keep them equal to each other as well. That mostly works just fine. So yeah, hopefully that makes sense. So the basic gist of it is, primarily affects memory timings, primarily affects memory speed. This one can sweet spot, this one doesn't really. This one just kind of scales indefinitely in my experience. Well, scales as long as you can cool it. I've gone quite, like, I've recently run DDR5 on actual LN2, and yeah, you can shove a lot of VDD into it with sub-zero temperatures. Anyway, the last voltage that the power management IC generates is VPP, and the only reason we really care about VPP is because it's stock, it's 1.8 volts. And the thing with this is VPP must always be higher than the MVDD and MVDDQ voltages, because VPP handles the word line of the memory chips, which is basically the thing that gates access to the actual capacitors that store your data. So if your VPP voltage is lower than MVDD or MVDDQ, your memory chips will not work correctly. Straight up, like, they will not work correctly whatsoever. They can also get damaged if your VPP is lower than MVDD or MVDDQ. And that's really most of it. So basically, the main reason you would care about VPP is, let's say you're running your memory, you're just benchmarking or something, and so you're going absolutely yeet on the voltages, even past what I would consider a brave voltage level. You're going to want to set your VPP higher. And honestly, you're least like, the nice thing is this comes really high stock, so I wouldn't be concerned going even as high as 2 volts again. And at this point, you should have more than enough voltage headroom for any DDR5 memory chips that are currently available, though maybe we'll see memory chips in the future that might scale to, like, insane MVDD or MVDDQ, in which case you might end up having to run, like, VPP at 2.2 volts or something. For DDR4, the VPP rail was sitting at 2.5 volts, which meant that you basically never had to worry about it, because DDR4 doesn't scale to, like, 2.4 volts anyway, so Yeah, but with DDR5, I think Samsung memory chips already sort of seem to be like I've seen people push them up to 1.75-ish volts, which makes me think that, yeah, if you're running Samsung memory at that kind of voltage, you're gonna probably want to raise this. Yeah, so that's kind of that. Now, the reason why this doesn't really affect overclocking is because the stock voltage level is so high that you're never going to be limited by how quickly the word line functions, right? Like, basically, regardless of what timings or memory speed you're running, it drives the word line circuitry so quickly that it doesn't matter. Like, going from 1.8 volts to 2 volts is not going to make a significant difference in the stability of the memory chip because it's already completing this task very, very quickly. So the only reason to ever raise it is to ensure that you have the headroom on the MVDD and MVDDQ voltages. So that's kind of that. That's all the different all the different voltages involved in DDR5 overclocking. And basically, the sort of simplified version of this is you can ignore VCC in. For your internal CPU voltages, I wouldn't recommend going above 1.45 volts ever. Well, no, if you're benching, you can go above that. But like, if you want your CPU to last a long time, I wouldn't recommend going over 1.45 volts for the internal voltages. For your memory sticks, if you want to, well, yeah, so for your internal voltages, 1.45 volts. For VDD2, you can go up to 1.6 volts, but it'll probably sweet spot somewhere between 1.2 and 1.45, so probably stick to that range to begin with. Though on some of the early gigabyte BIOSes, it actually scales to kind of silly levels, like 1.5, 1.55 even. And then for the actual memory voltages, generally, if you want to be extra safe, 1.4 volts is safe. And then if you're feeling brave, you can go up to 1.6 on your MVDDs, like VDD and VDDQ. So, yeah, that pretty much covers it for DDR5 voltages for overclocking. Hopefully this makes sense. Like the thing is, DDR5 basically, like for DDR4, you basically had this, right? Like this is what DDR4 is like. You had this and you had this, and that was it, because your VDD2 didn't just go to the CPU, it also went to the memory stick. But with DDR5, they decided to put a bunch of voltage, like, I'm still not entirely certain. Well, it simplifies the motherboard a bit. Doing this means that, like, especially if you're building a data center, having the power delivery on the memory stick means that you don't have to you don't need a motherboard with way more power delivery for the memory than you actually are going to use. You just need enough power delivery for the VDD2 rail, which is, much less than the actual memory sticks. So, yeah, which, like, there are server motherboards, because the thing is, for, like, DDR4 server boards, you could find, like, 4-phase memory power, because you have, I think it's 8 ranks on some of the, like, some of the registered ECC sticks can go up to 8 ranks of memory. And so you can end up with, like, half a terabyte of RAM on one side of the CPU, or even more than that. And turns out half a terabyte of RAM pulls a ton of power. So, yeah, so that's sort of the main reason why we have the built-in power delivery on the memory sticks, is if you're building a server, your memory sticks come with their own power delivery, so this stops being a concern. But for desktop applications, it's kind of like, this just makes life more complicated. So, yeah. Anyway, that's actually it for the video. Hopefully this makes sense and is somewhat helpful. If it doesn't, then I guess I'll have to reshoot this video. But, yeah, that's it. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you'd check them out and support me through them. And yeah, that's it for the video. So thanks for watching, and goodbye.